Hi, everybody. This is the first lecture from chapter 28, which deals with magnetic fields. In fact, in chapter 29, we'll finish up with another topic about magnetic fields and kind of finish up all of electromagnetism in the next chapter or so next week. But for this lecture, I want to first of all kind of define magnetic fields in terms of the force. So by a new field, it's similar to electric field in that it creates a force on a charge. But the force is calculated and acts differently on charges, as we'll see. So first of all, though, I'm sure probably a lot of you have dealt with permanent magnets at some point in the past, maybe a bar magnet with a north and a south pole. And so I just want to mention, in the next chapter, we'll talk a little more about how magnetic fields are created. But in this permanent magnet, it's really due to the motion of the electrons and the charges in the atoms. And generally speaking, you have to have an electric current creating a magnetic field, right? There's got to be some motion of electric charge to create a magnetic field. And in a permanent magnet, that motion is inside the atoms. But let's just look at what the magnetic field looks like. So outside the magnetic field, or outside the magnetic field goes from north to south, comes out of the North Pole and into the south. Inside the magnet, it goes the other way. It goes from south to north. Another configuration you can often have is that of a horseshoe magnet. Again, outside the magnetic field is going north to south, curves around here. So inside this region, the magnetic field is fairly uniform. And we're going to look for this chapter mainly at uniform constant fields. Of course, generally speaking, like the electric field, right? The electric field can curve, so can the magnetic field. Like it does around these. So an example of another magnet or magnetic field is, of course, the Earth's field. The Earth's field has a north and a south pole, and the magnetic field lines are around the Earth, kind of as if there's a permanent magnet or a bar magnet, a very large one inside the Earth. As an example of an actual electric current that creates a magnetic field, we'll eventually talk about a magnetic dipole. And the magnetic dipole is just a current loop. So it's got maybe a circle of wire with a current in it. And then the magnetic field comes out and curves around. And one thing you'll notice in all these cases, the magnetic field eventually has to form circles. It circles around and comes back in over here. So let's go on to, and one thing I should mention, I use the letter B for magnetic field, which is kind of the convention. But the letter M is often used for another quantity called magnetization. Let's go and talk about the force on a charge in a magnetic field. Sometimes magnetic fields are really a more three-dimensional thing than electric fields. So sometimes I want to draw the magnetic field going into the page or a magnetic field coming out of the page. I denote the magnetic field going in by X's. You can kind of think of them as the back or the feathers on the arrow shooting into the page. For a magnetic field coming out of the page, I use dots. And so you can kind of think of those as the tips of the arrows coming out at you. Right? So whenever you want to have a magnetic field going in or out, that's how I'm going to represent it. So let's talk about the force on a charge. This is the equation. Now, a couple things you'll first of all notice, it depends on the velocity of the charge. If the velocity of a charge in a magnetic field is 0, there is no force. It remains still. Depends on the charge, and so this is really the test charge, right? There are other charges, other currents creating the field, but we're talking about a charge that we're actually putting in the field and maybe moving with a certain velocity v. Now, the other thing is, of course, it depends on the strength of the field. And I've got this vector product, V cross B. This is called the cross product. And I'm going to try to define how to calculate that here in a second. Before that, though, notice the units, right? If I solve for B in terms of the units, it's a force over a charge times a speed, or a Newton per Coulomb meter per second. In the metric system, this has the name of Tesla. So the unit for electric field in the metric system is called the Tesla. It's equal to 1 Newton per Coulomb meter per second. Okay, so let's talk about the cross product. In general, you have two vectors, A and B. You multiply them to get a third vector, C. Now this is different from the dot product or the scalar product that we've done before, A dot B, because from that type of multiplication, you get a scalar, right? You don't get another vector. Now, to calculate this, I'm not going to go and prove this, but you'll find this kind of complicated formula for the components of the vector C. So you take AYBZ minus BYAZ, right? And these represent the Y component of A, the Z component of B. And you can use this formula to get the components. And this is written down in the book as well. We're not really going to use that much. Another thing you can prove from this is that the magnitude of this new vector C is equal to the magnitude, right, the length of vector A times the length of vector B times the sine of the angle between those two. All right, so if I've got vector A going this way and vector B this way, the angle that I'm talking about is the angle between the two vectors. And one thing you'll notice too is, what if the angle is 0? Well, if the angle is 0, the vectors are parallel. Sine of 0 is 0, the cross product is 0. So this is another unique thing about the magnetic force. If the charge is moving parallel to the field, right, into the board or into the page here on this one, the force is 0. It just keeps going straight along the field. That's very different than the electric force. Now it could be anti-parallel, right? Because 180 degrees, sine of 180 is also 0. So if it's either going with the field or against the magnetic field, the force is 0. It has to be at an angle. Now the maximum force is going to occur when the angle is 90 degrees. It's when the sine of 90 is 1, right? So how that I can get the magnitude from that. How do I get the direction? So we are going to use something called the right-hand rule. So I'm going to use my right hand, and I'm going to follow these 3 steps. So let me draw here a picture. I'm going to look at the case where I've got a charge moving perpendicular to the field. So let's say I've got a proton, a positive charge moving into the field with the speed v. My magnetic field is going into the page, right? So it's that way. V is that way. To the right, V is into the page. So how do I get the cross product V cross B? Okay, I use the first step. I put my fingers in the direction of V. Kind of hard to see. It's easier if I could stand in the classroom, but my fingers are going to the right. Now I face my palm in the direction of B, which means I put it flat on the page, right? It's like magnetic field's coming out of my palm into the page. Then the third step is that for a positive charge, my thumb gives the direction of the force, or the cross product. So in this case, the force would be upward on my positive charge. Now it's at 90 degrees to both V and B. That's always the case, right? So it's kind of always a 3-dimensional thing. You've got V going one way, B going another, and the force going the other way. Now, what if it was a negative charge? If it was an electron, well, you can still use the right-hand rule, but just at the end, add a 4th step, right? Flip your thumb over, because negative charges do the opposite of positive charges. It would go down instead of up. So let's talk a little bit more about this magnetic force here. Leave that one later here. In a magnetic field. So let's draw this again. I've got my magnetic field going into the page. And I'm going to shoot my proton in, my positive charge. Now, the force, as we said, using that right-hand rule, is going to be going upward. Now, the force will cause the charge to be pulled upward. So eventually, after a little bit, it'll now be going at an angle, right? It's going to get pulled up. What happens then? Right hand rule, fingers are now kind of at an angle here, palm still down. My force is still perpendicular to V. So maybe what you can see is that this force will continuously change direction. And in fact, this charge will end up moving in a circle around the magnetic field lines, a circle with a radius r. As it turns out, magnetic force is what we call a centripetal force. It causes charges to go in a circle. Now you could have, instead of the charge going straight parallel, what if it was kind of going at an angle into the page? Now it's kind of coming to the right, but also has a component going into the page. Well, it would still circle, but it would actually keep going along the field lines. It would kind of spiral or form a helical motion around the field lines. Right? And maybe I could draw it over here. Say I had my magnetic field going up. So now I've kind of, instead of going in, I've kind of tilted everything. Where you could see that the charge would kind of spiral around the field lines. And we call that a helix, or a helical type of motion. One question we'll have right now, though, is, well, what size is the circle? What is the radius of that circle? How does it depend on the mass of the charge and the other aspects like the speed, the velocity, and the magnetic field strength? Well, in this case, my angle is 90 degrees, so my magnetic force is QVB, right? Sine of 90, which is 1. Like I said, it's a centripetal force, so it's going to equal mv squared over r from physics 221. We could solve for the radius now, right? One of the v's cancels. We just have r is equal to mv over qv. So we see that the radius of the charge depends on the mass and the speed. The faster it's going, the bigger the radius. The larger the mass, the larger the radius too. Right, and that makes sense because of inertia. I mean, it's going to be harder to turn something with larger mass. The bigger the charge, though, and the bigger the field, the smaller the radius, the tighter things, the circle it makes. Now, if you just left everything alone after it gets in the magnetic field, it would just keep circling, and we can talk about a frequency. Right, what is the frequency at which it rotates around in that circle? Now the frequency is related to the time it takes to actually make the circle, and we call that a period. So the period is the time it takes to go all the way around one time. The frequency, F, is 1 over the period. It's the number of times it goes around each second. Another quantity that's often used is angular frequency. Right? And so for angular frequency, we call this, or label it with the Greek letter omega. It looks like a W, but it's equal to 2 pi times the frequency, 2 pi f. So it's really the radians per second that it's going through. So what is omega for this case? Well, let's think about the period first. The period is the time it takes to go around one time, right? And that's going to be distance over velocity, or 2 pi r, circumference, over how fast it's going. Now the speed isn't changing, right? It's going at a constant speed, like it does in a centripetal type of force problem. So here's my period. My frequency is 1 over that. So I can write 2 pi, for my angular frequency, 2 pi times v over 2 pi r. Let's see. So let me see here. I think I've got the right answer there. Hold on 1 second. Let me just make sure I've got the right formula, because that doesn't seem to make sense unit-wise. Yeah, I guess actually it does. So basically we can just get V over R, but what we can do is plug in our value of R. So when I plug this in for R, I have V over MV over QB, and when I flip it over, it's QB over M. All right, so this is the radians per second that the charge is moving around. This is the radius of the charge, or of the circle that it makes. So one thing you can tell, right? I mean, this is one way that you can determine maybe things about the charge. One thing that you can tell is what the mass of the charge is. So let's talk about that a little bit. Sometimes people use what are called mass spectrometers to determine mass. So let's say I'm going to do another example here of a field coming out, just to practice the right-hand rule here a little bit. So my magnetic field's coming out. Let's say I shoot my proton, my positive charge, with a mass P of 1.7 times 10 to the negative 27 kilograms. Okay, so what way is it going to go? Again, right-hand rule, fingers are up. That's the direction of V, the speed of the charge or velocity of the charge. Now my palm points upward because the field is coming out at me. My thumb is to the right. So for a positive charge, it's going to circle kind of like this. Right? Now, of course, if it leaves the field, then it would go straight. But the point is that from the size of the circle or the distance it hits over here, I could tell kind of the relative mass. What if it was an electron? Now, if I had a negative electron and the mass is much smaller, 9.1 times 10 to the negative 31 kilograms, what you would see, let's say it was going at the same speed, well, it would make a much tighter circle, right? Because it has much smaller mass. So in fact, you could, if it circled, it would make a much smaller circle than the proton would. So you can see, I can somehow use the magnetic field to get the mass information of the charge. And we call this mass spectrometry. Now, interestingly enough, just historically, this is how a lot of charged particles were first discovered. The electron was first discovered by J.J. Thomson in 1897 by shooting a beam of electrons and seeing how they deflected in the magnetic field. Interestingly enough, back in the 1930s, people were trying to study radiation that ends up as like somewhat radiation comes from the ground, some comes from the sky, but what they used was something called the bubble chamber, which is a really low pressure gas. And if you have a charged particle go through this, it'll form bubbles and make a track. So you can actually see the path of the charge in the bubble chamber. So what people would do is they'd set their bubble chambers out on their lab table, and every once in a while take photographs, and they would see these tracks of charges that have moved through. Some of them are protons that come from cosmic rays from space. Charged particles, there are different kinds. Around the same time, quantum mechanics was being developed, and a physicist named Paul Dirac had tried to combine the theory of relativity and quantum mechanics and had predicted another particle. He predicted a particle that had the exact same mass as the electron, but was positively charged. So he told these physicists with the bubble chambers, hey, go look and see if you can find this. And sure enough, pretty soon they found a track that was exactly the same as the electron, just the other way, right? And today we call this positive electron a positron. So this is how the positron and antimatter or antiparticles were actually discovered, was in terms of watching the path of the charge in this magnetic field. So one last application of this, let's look at what if we had both an electric and a magnetic field together, and we want to shoot an electron through that region where we've got a crossed electric and magnetic field. Right, and so we're shooting these at a certain speed. The way you could get electrons to a certain speed is to move them through a voltage and accelerate them. Maybe we'll talk about that in another video or in a problem. But we get it up to a certain speed, and once it comes in, right, it hits this region where I've got crossed electric fields and magnetic fields. Now the magnetic field, I've drawn X's. It's going into the page. The electric field is going down. It's kind of like the capacitor plates here with a positive charge here and a negative charge down here. So what happens? Okay, so the electron, right hand rule, V this way, palm in, right, because the magnetic field's going in, but it's a negative charge, so I have to flip my thumb over. So the force from the magnetic field is going to be downward. What about the electric field? Well, the electric field, negative charges go opposite the field, so the electric force is here. It's going up, right? Now, depending on which force is bigger, which field is bigger, the electron will come out and hit somewhere over here on the screen somewhere. But let's say you wanted to get a certain speed of electron, right? I mean, where it hits is going to depend on how fast the electron's going too. So say you wanted an electron to come directly through and hit right in the center over here. What speed would it have? Well, let's look at our forces. We've got a positive upward QE electric force, and we have a negative or downward QVB magnetic force. The Q cancels, and I can solve for V. So V is equal to E over B. So this is a way I can actually measure the speed of charged particles, right? I just adjust my electric and magnetic fields until it hits in the center of the screen, and I can calculate the speed that the charge must have. This is kind of a simplified version of what J.J. Thomson did to discover the electron. That's J.J. Thomson, Thomson, in 1897. He used the cross electric and magnetic field to measure the size of the circle or where it hits on the screen. And then going back from that, was able to get the charge to mass ratio of the electron. So if you want to read about J.J. Thomson, I won't go into more detail on that, but magnetic fields are essential for studying subatomic particles. In fact, in another video, I may talk about cyclotrons and synchrotrons, which are used to accelerate charges up to extremely high speeds. And they've led to a lot of discoveries about new kinds of subatomic particles, right, that you don't see every day. You'll see only when you collide these things in these big accelerators. But hopefully that will help with doing the problems on magnetic force, charge in a magnetic field. In the next video, I'll talk about what if you have a current in a magnetic field.